Good morning. So, welcome to Chemipedia, chemistry classes for 11th and 12th standard. In this video, I am going to discuss about the postulates of valence bond theory. That is postulates of V.B theory. Okay. There are 10 postulates in valence bond theory. So, let us discuss one by one. Okay. You know that in complex compound, so central metal ion is acting as an electron acceptor, Lewis acid, and the ligand is a electron donor, Lewis base, which means that ligand shares the electron with the central metal ion such a way it makes a bond with the central metal ion, isn't it? Right. According to V.B theory, the bond formed between ligand and metal, is covalent in nature. So first postulate says that the nature of bond what we have between metal and ligand. So the nature of bond is covalent because this bond is formed by sharing of electron. This bond is formed by sharing of electron between metal and ligand. Correct. Point number 2, ligand possesses filled orbital. Because ligand being an electron donor, it is supposed to have electrons to donate to the central metal ion, isn't it? So which means that ligand has a filled orbitals with at least one pair of electron, which is to be donated to the central metal ion. Okay, right. So that is a second postulate. Ligand must possess filled orbital with at least one pair of electron because the ligand is basically behaving as an electron donor, donates electron to the central metal ion. At point number 3, central metal ion should possess empty orbital, vacant orbital, which is equal to the coordination number of the central metal ion, because in complex compounds central metal ion acts as a electron acceptor, that is Lewis acid, isn't it? Which means that it accepts electron from ligand. So each ligand is donating a pair of electron to the central metal ion, isn't it? So that to accommodate the electron which is shared by the ligand, the central metal ion is supposed to have vacant orbitals, which is equal to coordination number. Okay, right. That point number 3. Then point number 4. So the central metal ion and the ligand, before they form bond between them, the vacant orbital of central metal ion undergoes a process called as hybridization. So before bond formation between metal and ligand, there is a process called hybridization takes place in case of central metal ion. So what is meant by hybridization? It's nothing but process of mixing of orbitals with comparable energy to form new orbitals, to form equal number of new orbitals with same energy is what we call it as hybridization. Which means according to valence bond theory, the central metal ion undergoes hybridization, which means the orbitals which are having comparable energy of central metal ion undergoes hybridization process, and they are converted into a equal number of new orbitals with same energy, and those orbitals which are newly formed are called as hybridized orbitals. Okay, right. Then once the hybridization is completed, then the hybridized orbital of central metal ion undergoes linear overlapping with the filled orbitals of ligand, which means that hybridized orbitals and filled orbital of ligands are sharing the electron between them. So that sharing of the electron between ligand and central metal ion occurs by overlapping process, whereas the overlapping is in a linear manner. So generally you know that linear overlapping of orbitals will result in formation of sigma bonds. Okay, so the hybridized orbital of central metal ion undergoes linear overlapping with filled orbital of ligand to form coordinate covalent sigma bonds. Okay, right. So this is a point actually. So before bond formation, metal undergoes hybridization. Once the hybridization is completed, then the electron sharing takes place between hybridized orbitals of metal and filled orbitals of ligand. Okay, right. Next point number 6. The hybridized orbitals are directional in nature. Once hybridization is completed, the new orbitals formed, what we call it as hybridized orbital, they have different spatial orientation. They are arranged in a different way around the central metal ion, and they give a particular geometry to the complex salt. So that the hybrid orbitals are called as directional in nature. They are directional in nature, which means they are responsible for geometry of the complex. Okay, right. So now you are given a list of complexes with their nature of hybridization as well as geometry. Okay, right. In a complex, if coordination number of central metal ion is 2, that follows sp hybridization, then the geometry of the complex will be linear. So and I have given one example for each type. Okay, so CuCl2 with minus charge is example for a complex with coordination number 2 which follows sp hybridization with linear geometry. Okay, similarly, if coordination number of the complex is 3, it follows sp2 hybridization. Geometry is trigonal planar, and this is an example for that. If the coordination number is 4, the hybridization may be either sp3 or dsp2. That depends upon the nature of lecon what is present in the complex. Suppose the lecon present in the complex is of weak field lecon, probably the complex may have sp3 hybridization with tetrahedral geometry, and this is an example for that mostly. Then if the complex with coordination number 4 undergoes dsp2 hybridization, what is it? dsp2 hybridization, that is maybe due to presence of strong field lecon, then the complex attains square planar geometry, and this nickel cyano complex is an example for that. For tetrahedral geometry, another example, NiCl4 2 minus. You can remember even the other example, NiCl4 2 minus also. Correct. Then coordination number 5, the hybridization is dsp3. Geometry is trigonal bipyramidal. Cyan pentacarbonyl is example for that. If coordination number is 6, the complex may undergo either D2sp3 or sp3d2 hybridization. Whether hybridization is D2sp3 inner d orbital or sp3d2 which involves outer d orbital, the geometry is nothing but octahedral. Okay, right. And FeCN6 4 minus, example for D2sp3 hybridization. Then FeF6 4 minus for sp3d2 hybridization. Okay, so this is nothing but list of complexes with different coordination number and their hybridization followed by their geometry. Okay, right. The next postulate, in octahedral complexes, that is complex with coordination number 6 is octahedral in shape geometry. There are two types of octahedral complexes. One is called inner orbital complex, another one is called outer orbital complex. The other name of inner orbital complex, low spin complex or spin pad complex. Similarly, outer orbital complex has another name, high spin complex, spin free complex. So what is the difference between inner and outer orbital complex? So generally, in octahedral complex, they undergo either D2sp3 hybridization or sp3d2 hybridization, isn't it? Right. Suppose if n-1 d orbital take part in hybridization, then it is called as inner orbital complex. If the d orbital which participate in hybridization is nd, if nd orbital undergo hybridization, then it is outer orbital complex. Okay, so I have given an example. Look at this. If 3d, 4s and 4p orbital take part in hybridization, that comes under inner orbital complex. If 4s, 4p, 4d is the orbitals which involves in hybridization, then it is called outer orbital complex. See here, 3d orbital, which is inner d orbital, isn't it? So the hybridization involving 3d, 4s, 4p, inner orbital complex. Look at the next one, the 4d orbital, which is outside of 4s and 4p. So hybridization involving 4d is forming outer orbital complex. Okay, right. So this is point number 7. Then point number 8, the complex compound may be either paramagnetic or diamagnetic, which is depending upon the presence or absence of unpaired electron. Suppose if a complex has at least one unpaired electron, then it behaves as paramagnetic. If there is no unpaired electron, a complex without unpaired electron behaves as diamagnetic. Point number 9. In case of licons, there are two types. One is strong field licon, another one weak field licon. So what is the difference between strong field and weak field licon? So strong field licon can cause pairing of the single electrons which are present in the central metal ion. So in presence of strong field licon, if there are any unpaired electron in the central metal ion, they are getting paired up. Okay, pairing takes place in presence of strong field licon. So these are some examples for strong field licon: cyanido, Cn minus, CO and NH3. So presence of these licons will pair up the single electrons, unpaired electrons. Weak field licon cannot do that process. It do not cause pairing of electron. Okay, right. So now halide licons and nitrito, oxalato. So these are example for weak field which doesn't cause pairing up unpaired electron of the central metal ion. Okay, the last point, when covalent bond between metal and licand is formed, that takes place with overlapping of the hybrid orbital of central metal ion and filled orbital of licans, isn't it? So if the overlapping between those two orbitals is greater, then a strong covalent bond will be formed between metal and licand. Okay, so that for the formation of strong covalent bond between metal and licand, the overlapping of orbital should be maximum, or overlapping should be greater. Okay, right. So these are the various postulates of valence bond theory. Okay, like Werner's theory, even valence bond theory also has some limitations. Okay, like the previous theory, this also does not explain anything about color of the complex. Okay, right. And the second limitation, it explains only spin magnetic moment. So with the help of valence bond theory, we are able to calculate spin magnetic moment of a complex salt, but it does not explain the other components, whereas the other components of magnetic moments were not explained by this theory. Okay, so this is another limitation. The third limitation, is not giving any explanation. This theory is not giving any explanation why same metal is forming both type of octahedral complex. So when a central metal ion forms octahedral complex, in some case same metal ion is capable of forming both inner orbital complex as well as outer orbital complex. So why this happens? Why same metal ion forms both inner orbital and outer orbital complex? That is not explained by this valence bond theory. Okay, so as example, this complex Fe(F6) 3 minus and FeCN6 3 minus. In both the case, the central metal ion is nothing but Fe3 plus ion, ferric ion. Okay, right. The first complex is outer orbital complex. First one is outer orbital complex, in which outer d orbital take part in hybridization. The second one, FeCN6 3 minus, is inner orbital complex. So now you can see the same metal ion Fe3 plus forms both type of complexes. Why this happens is not explained by Werner's theory. Okay, so these are the three limitations of this is not explained by valence bond theory. So these are the three limitations of valence bond theory. No information regarding color, not explaining other components of magnetic moment, why same metal ion is forming both type of complexes. Okay, right. I hope you understood about the various postulates of valence bond theory. Right. Thank you.